Hi, this is Dave Johnson with another edition of Math Off Topics. Uh, a few videos back, I derived the expression for E, and I think I made a statement then that it was possible to prove that E exists. And so in this video and in a related video, and I will show links to these relevant videos in the show notes below, I derive or prove that E exists. So the first part of that proof is to show that the expression involved is monotonically increasing. And then the second part is going to be to show that the expression is bounded above. And I'll do that in a separate video. Okay, so let's get into it. So the expression that I'm talking about is 1 plus 1 over p raised to the p. And I actually had a different expression in my other video, which was 1 plus, say, x raised to the 1 over x, but you can see immediately that those are equivalent depending on whether your x is going to 0 or x is going to infinity. Here, we're assuming that x is going to infinity. And so notice first that this is a binomial raised to a power. And that power, p, if p were an integer, we could just simply use uh, the regular binomial theorem, which a lot of people see in high school or some algebra course. But I don't find that proof to be very satisfying. I'd rather not limit myself to integer values of the exponent. I'd rather have real values. So the better way to do this, I think, is to use the generalized binomial theorem. And so let me write that down. So 1 plus x, and that's a binomial. Let's use the power p. It's the same symbol, it means the same thing. So this is equal to 1 plus px plus 1 half p times p minus 1 x squared plus 1 over 3 factorial p times p minus 1 times p minus 2 x cubed plus, and some more terms. Now I want to go here and say let's consider a kth term. So 1 over k factorial times p minus 1 times p minus 2, and then some more factors, dot, 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 p minus, and let's just go ahead and write it this way, k minus 1, and then times x to the k. And then some more terms after that. So there's an infinite number of terms. We're considering the kth term. And what do I mean by the kth term? Well, in this expansion of the binomial, we get this term here, and I'm going to call that the kth term. And in fact, let me go ahead and write it this way. So 1 plus x raised to the p, but we'll call this the kth term, is equal to 1 over k factorial. And then the rest of this, p times p minus 1 times p minus 2, dot, 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 times p minus k minus 1, and then times x to the k. So that is the kth term of our expansion. Now, I'm going to go ahead and anticipate where we're going with this. So first of all, we want this value here, the 1 over p, to be the reciprocal of this value, p. And so let's just go ahead and replace x with 1 over p. So 1 plus 1 over p, and we're only going to look at the kth term. So this is equal to 1 over k factorial times p minus 1. I know it's a lot of writing. When you get into higher mathematics, you get used to this kind of stuff. p minus k minus 1. And then x gets replaced with 1 over p. So this is 1 over p raised to the kth power. Now, a lot of what I'm doing right now is sort of preliminary, just kind of setting the stage for where we're going. Notice that this 1 over p to the k, that could be rewritten as 1 divided by p raised to the k. So I have k factors of p downstairs. And notice I have 1, 2, dot, 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 k minus 1, but then you add this one, that makes it k factors. And we've got just enough factors of p that I could divide every one of those factors by p. And if we do that, p divided by p is 1. P minus 1 divided by p is going to be 1 minus 1 over p, and so on. So let me write those down. So, and let me just carry my left side with me. 1 over p raised to the p, and this is the kth term. The 1 over k factorial doesn't change. Now the p divided by p is 1. I'm not going to write that factor. P minus 1 over p gives us 1 minus 1 over p. The p minus 2 divided by p gives us 1 minus 2 over p. Dot, dot, dot. I think you guys see where this is going. 1 minus, and then k minus 1 over p. And the 1 divided by p raised to the k, well, that got used in dividing out all those terms. Okay, cool. Now, what we really want to do is we want to go back here and we want to show that this is constantly growing. And so the way you do that is you say, well, pick a small value of p and a big value of p, plug them in and compare terms. So if we do that, let's say that b is greater than a, and that all these numbers are greater than 0. So I'm going to plug in for p. I'm going to plug in b. So we get 1 plus 1 over b raised to the b, the kth term. So that's 1 over k factorial. And we're getting better at writing this, right? 1 minus 1 over b times 1 minus 2 over b, dot, 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 times 1 minus k minus 1 over b. And let's do the same thing with a. So 1 plus 1 over a raised to the a, and we're looking at the kth term. So this is 1 over k factorial. Again, that doesn't change. 1 minus 1 over a times 1 minus 2 over a, dot, 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 times 1 minus k minus 1 over a. Now here's where the rubber meets the road, because all we have to do is compare these two terms. And I'm going to make the statement that because b is bigger, the 1 over b is smaller, and so this factor is actually going to be bigger because you're subtracting a smaller amount. The same here and the same here. And so, and k factorial doesn't even enter in to this consideration. So this term, the kth term of 1 plus 1 over b to the b, is going to be bigger than this term here. So let me write that. So if b greater than a, then 1 plus 1 over b raised to the b the kth term is going to be greater than 1 plus 1 over a raised to the, I didn't mean k there, I meant the b. I'll get there. B, this is a. And so this term is bigger than this term. This is also the kth term. And this is true for all k. Therefore, 1 plus 1 over p raised to the p is monotonically increasing. Monotonically increasing. Because when you increase the size of your p, the expression gets bigger. Now, as I said, I will do the second half of this proof in another video. I hope this was helpful. If you enjoyed this video, please like and subscribe, and I'll see you in the next video.